Hello students, welcome back to A-Star Tuition channel. Today, we will continue our discussion about circular motion and gravitation part 2. Specifically, we will discuss about gravitational force, field, and potential. Let's start. We will begin our discussion about gravitational force. So, this is what we call as Newton's law of gravitation. Now, this law was discovered by Newton in the 1600s. Now, in the 1900s, in the early 20th century, Einstein actually came up with a more general theory about gravitation that explained gravity with more insight. However, Newton's law of gravitation still holds in a lot of macro phenomena like orbital motion, and also it explained about how gravitation works without really discussing the origin or the nature. So without further ado, let's just write down the universal law of gravitation by Newton. So basically, the law stipulates, this is the content of the law. When you have two objects that have masses, they are separated by a certain distance from each other, then there is a attractive force which is proportional to the product of the mass but inverse proportional to the square of the distance. So we can say that when two objects are separated, when two objects with mass, so having mass, so two objects having masses and separated by distance, then attractive force between them is directly proportional to the product of the masses, proportional to the product of their masses, and inversely proportional to the square of the distance. Inversely proportional to the square of the distance between them, square of the distance. Now from here, we can see that if the two objects are separated at longer distance, the amount of force is weaker. So mathematically, we can write the force is proportional to, this is the first, the mass of the first object times the mass of the second object, and then you divide the whole thing with the square of the distance. So inverse proportional to the square. Now this equation becomes, remember this is not equation yet, this is only relationship. Now in order to make this equation intact or complete, we need to multiply with constant of proportionality, and that constant of proportionality is g. So now we can write down as g m1 m2 over r. Now this is the capital G here, is the Newton's universal constant of gravitation. And this has a value in lab, discovered in lab, and the value is 6.67 times 10 to the power of minus 11 Newton, kilogram minus 2, and meter square. Now let's discuss further about this equation. So let's say that you have an object, the mass is m1, and then you have another object, the mass is m2. So what happens is that, and then they're separated by a distance of r from the center. Yeah. Now, before I continue, I should also mention that this law actually applicable to point particles. Now, what does it mean by point particles? Point particle means that particle that whose size is negligible. Now, obviously, you know that in real life there are no such thing as point particle. However, I want you to understand that in some situation, even a very large object can be considered point particles. For instance, so this is the Earth, right? Now the Earth is obviously not point particle in the usual sense. But then let's say that this is the Moon, right? Now, so this is the Moon and this is Earth. So then, because of the very large distance separating the Earth and the Moon, that if you hypothetically can view Earth and the Moon from a certain other location, then the Earth and the Moon can be more or less considered as point particle. Yeah, so you can also imagine this, like let's say that you are you're taking an airplane, and then you are about to land in a airport in a city, for maybe another 15-20 minutes, and you probably from a distance, from the comfort of your airplane seat, you can probably feel that there are actually some buildings. So this building on one side of the town, on this building on the other side of the town, that looks very, very small, so that you see that the reason is because they're actually at a very large distance. Now obviously when you approach one of the building, then you see obviously they are huge building, yeah. But then at a certain point of view, then because of this large distance, we can actually make the assumption that those are point particles in this context or in this situation. So if you have, let's say, Earth here and the Moon here, for instance, even though they are not point particles by any stretch of by any means of the word, but at least at far away distance from each other, and then you sit back and at other location, you can see that because of this large distance compared to their individual sizes, you can actually see that actually the assumption of point particle can be used in this situation. Now let's go back to this. So m1 is the mass of the first object, m2 is the mass of the second object. They are separated by a distance of r. So the force between them is going to be attractive in nature, and the value is given by this. Yeah. Now, I want to show to you that the force on m1 due to m2 is this way, and the force on m2 due to m1 is this way. Now, you see that the force is the same. This force and that force, they have the same magnitude but opposite direction. So these are what we call as, remember in the previous topic about Newton's law of motion number 3, for every action there's equal opposite reaction. So these two forces are action and reaction in nature. Yeah, so hopefully you understand the concept. Yeah, so the force on m1 is this. We can write it as label as F12. F12 means force on 1 due to object 2, and F21 is force on object 2 due to object 1. Now consider this situation. So you have, let's say, 3 objects whose masses are m1, m2 and m3 respectively, and there's distance of r12 between the first object and the second, and r23 between the second and the third. Now the question that could arise from this situation is, what is the magnitude and the direction of the resultant gravitational force on M2. Remember, this is force, it's a factor. So in order to answer this, please understand that M2 is attracted to M1, so the direction is going to be to the left. Now this is called F21, which means this is the force on 2 due to 1. And also here you can see that there is mass 3 to the right of M2, so M2 is attracted to the right by force F23, which is the force on 2 due to 3. Now the equation for each is given, so we can just write down here as G M1 M2 divided by R12 square, and then F23 would be G M3 M2 over R23 square. Now look at the direction. So one is to the right and another is to the left. So usually we use right as positive and left as negative. So in that case we can put a minus sign here and then plus sign here to get the resultant force on M2. Okay, so hopefully you understand this. So but then also it's possible to choose left as positive if we already know that the force that is going to the left is greater. But in general it's fine to use this, as long as we're consistent with the direction. So now the resultant force of these two, this is easy, you can just calculate them, and because these two forces are collinear, so they're in the same straight line, so you can simply find the value and then subtract, and then whichever greater, if F23 is greater than F21, then the value should be positive, which means that the resultant force is to the right. However, if F21 is greater than F23, then the resultant is to the left. Now what about the three objects are configured like this? So M1 is directly above M2 and M2 is to the left of M3. So then in order to find the resultant force on M2, this is just to find the resultant force of any factor that you are familiar with. Now in this case it's actually quite simple because you already have the horizontal, because remember M2 will be attracted this way, and this is going to be F12, and also attracted to the left and to the right by due to M3, F23. So the horizontal and the vertical, the vertical component are already there. So all you need to do is to find the force by using this formula. Remember, please use the appropriate value. So for instance, you want to find F23, then use M2 M3 over R23 square. If you want to calculate F12, use M1 M2 over R12 square. So and then here in this case, because F12 is what you call it vertical and F23 is horizontal, you can just use this to find the resultant force, and then you can find the direction by using tangent of alpha equal to F12, because this is the vertical and this is the horizontal. Actually this is not F12, F21, F21, because force on 2 due to 1. Okay, F21. Now once you get this, then alpha can be calculated based the actual angle can be determined by using the quadrant consideration. Hopefully you still remember how to do this. So this is 360. This is 180 minus plus alpha, and this is 360 minus alpha, or simply minus alpha. So again, in this case, one factor is horizontal and the other is vertical. So you can just do it this way. Now, if it's a bit more complicated, then what you can do is you can resolve it horizontally and vertically, and then find the sum of the horizontal forces and find the sum of the vertical forces, and then you use this. So again, please remember how to do this when we discuss about how to do this in factors, yeah, in the factors unit. Now, another problem that you can consider is this. So you have two masses, two objects, m1 and m3. They are separated by a distance of d. Now the question is this: I have another object, yeah, m2. The question is, where should I put m2 along the line connecting m1 and m3, such that the gravitational force acting on m2 is 0? So remember, for the example that I showed to you, the first one, is that if you put m2 in between m1 and m3, it will experience gravitational pull from each of the masses. So obviously m2 must be in between m1 and m3. Yeah? You cannot put m2 here. If you put m2 here, m2 will be attracted to m1 and will be also attracted to m3. Yeah? So then these two forces will not cancel. Yeah? But if you put m2 somewhere in between m1 and m3, then one force goes to the left and the other force is attracted to the right. So then they can cancel. Now, so the only way so that they cancel is that the amount of the force itself are equal. Now, what I mean is this: you know that if you put m2 in between m1 and m3, m2 will be attracted to m1, yeah, and the direction of the pull is to the left, and also be attracted to m3, directed to the right. Now, in order for the gravitational force is 0, then these forces must equal in magnitude. In other words, let's say that the point in which the point in between m1 and m1 and m3, such that the gravitational force on m2 would have been 0 is, let's say, here. So this is x. And so here I choose it to be closer to m1, but then it actually doesn't matter. It could be closer to m3 or it could be in the middle. Yeah? So then if this is m2, let's say you put m2 here, then the gravitational force acting on m2 due to m1 is F21, and it's equal to minus, because it's to the left, minus g m2 m1 over r12. r12 is x, yeah? So the distance between m1 and m2 is x. Now, as for the force acting on m2 due to m3, it's going this way. Now we call it F23. So it's plus because it's to the right. G m2 m3 over, now the distance is equal to what? The distance is obviously equal to d minus x squared. Yeah? The reason why it's that, because remember, m1 and m3 is separated by d, but m1 to m2 is x, so then the remaining distance from m2 to m3 is simply simple subtraction, d minus x. So then this must equal to 0 in order to for the resultant gravitational force on m2 0. Yeah, so then we can solve this. If we move this to the other side, we get g m2 m1 divided by x squared. This is equal to g m2 m3 divided by d minus x squared. And what we can do from here is we can cancel common quantities or common variable. So g cancel, m2 cancel. Now we want to solve for dx here. What is x in terms of d? So here you have m1 over x squared equal to m3 over d minus x squared. Now we cross multiply, we end up with d minus x squared over x squared, that's equal to m3 over m1. Now in order to find d in terms of x, we can take square root of both sides, so this becomes d minus x over x equal to the square root of m3 over m1. And then let's call this alpha, yeah. So alpha, so that we can, let's absorb this as alpha, absorb this variable. So then you cross multiply d minus x equal to x alpha, d is equal to x plus x alpha, d equal to x1 plus alpha. So the x equal to d over 1 plus alpha, aka d over 1 plus root of m3 divided by m1, root of m3 over m1. Yeah, so this is the x. Yeah. Now, so here, what you can learn from this is that if m3 is equal to m1, what happened? m3 over m1 will be 1. So this factor would be 1, and then d, it's going to be, the x is going to be d over 1 plus 1, which is d over 2, which makes sense, yeah? Because when m1 and m3 are of equal magnitude, then the only point you can put m2 is right in the middle. Because remember, the gravitational force has a strength that is proportional to the, the product of the mass and inverse proportional to the distance. So if they both have the same mass, then the position of zero resultant gravitational force on m2 should be right in the middle. Now what about if it's closer to m3? I'm sorry, let's say what happens if m3 is greater than m1. Now if m3 is greater than m1, then logically, if you put m2, let's say, if you put m2 in the middle, then the force on m2 due to m3 would be greater. Because remember, if m3 is greater than m1, but the distance are the same right in the middle, for instance, then obviously the resultant force won't be zero, because the pull from m3 is greater than the pull from m1. So in order to make it zero, you have to move it to the left, a bit to the left. Yeah, so it's easy to see from this equation, m3 greater than m1, so this will give you something, what, greater than 1. So d divided by 1 plus something, so divide by something greater than 2. So if you divide by something greater than 2, then obviously it will shift to the left. Now let's talk about gravitational field. Yeah. So what is gravitation? We already talked about gravitational force. Now what is field? Now gravitational field is this is actually not an abstract concept. Yeah. So some student in the past used to talk like this is an abstract. It's not abstract. Gravitational field is actually can be understood like this. So imagine that you are in a certain location. Yeah, it could be inside your room, or it could be someone in outer space, or astronaut inside a spacecraft. Now, any location in which an object that has mass experiences gravitational force is what we call as gravitational field. So let me define. Yeah. So gravitational field can be defined as location, any location, yeah, in space where objects, any object that has mass, any object that has mass would experience gravitational force. Yeah. So in this case, we know that the gravitational field is produced by some sort of large body of mass in the vicinity of that large body of mass. Yeah? So location in space where any object that has mass would experience gravitational force. That is what gravitational field is about. For instance, this room, yeah, I know that this room is a gravitational field. Yeah? this eraser, yeah, if you let it go, what happens, it will fall down. That is because of the gravitational field produced by our Earth. And remember, Earth is actually a very large object, yeah, object with, you know, with a tremendous amount of mass. So therefore, it produces, you know, some gravitational field. Okay, so location in space for any object that has mass with exponential gravity, that's gravitational field. Now, there is an associated quantity to gravitational field, but this is actually called the gravitational field strength, G. Now, this gravitational field strength is something that we already encountered when we discussed about vertical motion in kinematics, and also when we discuss about Newton's law of motion, the weight thingy. And we know that from that lesson, gravitational field strength due to Earth, at the surface of the Earth or at a location that is vertically more or less 1 kilometer, 1 kilometer or less from the surface of the Earth, is approximately 9.81 meter per square second on average. Yeah. Remember, every location on Earth will have different value, but then on average is 9.81. However, this is now that is actually the the G that I introduced to you before is taken to be uniform, but in reality it's actually not uniform. Yeah. So how do you quantify? Let's discuss the definition now. The definition of gravitational field strength is actually force per unit mass acting on a test mass that is located in a gravitational field. Yeah. So this definition is actually an operational definition. You can actually calculate by using Fg divided by m. Now see how similar this formula is with the formula of weight. Yeah, so mg. So it makes sense because any object that is located on Earth or earthbound mass multiplied by g, you get the weight. Yeah. So this is gravitational field strength. Now please understand that these two terminology are actually different. Yeah, not the same thing. This is about the space itself, and this is about the strength of the field. Yeah, this is the field, this is the strength of the field. So it's a bit different. So if a question asks you to define gravitational field, this is how you're supposed to define it. And if a question asks you to define gravitational field strength, then you define it this way. Remember that sometimes, depending on context, these two can be, sometimes we can use this to mean that, but that's actually, you have to be careful, yeah, because field and field strength are two different things. But then again, at some situation, when you look at when you read a problem, when they mention calculate the gravitational field, so then you know that what they mean is the gravitational field strength, because you don't actually calculate gravitational field. There's nothing to calculate for gravitational field. It's location, the space. Yeah. Now let's quantify this. Yeah. Discuss this further. Now remember that if you have two masses, we just discussed this before. Yeah. For gravitational force between two objects, m and m. One capital M and another is lowercase m. Let's say that they are separated by distance r from each other. So you know that the gravitational force acting on on each other is g mm over r squared. Now, if you want to calculate what is the gravitational field strength at the location where the lowercase m is located, yeah, due to the existence or due to the location of m here, the capital M, you just divide this by lowercase m and this will cancel. It's going to give you gm over r squared. So this is the formula for the gravitational force, the gravitational field strength produced by this large mass or capital M at a distance r away from it. So in other words, if let's say that this is M, yeah, it produced gravitational field strength, and the magnitude is it depends on what the M value here is, and also look at the distance, inverse proportional to distance. Yeah? Now, because this is a force, then it's a vector. Yeah? So therefore, you can see that you can draw the vector like this in all location. Yeah, radial in all location, all direction, I should say. And not only this, yeah, you can actually draw another. Let's say here. Now, when you draw at location that is further, you can see that when you draw the arrow is shorter, and this is to indicate that the field strength is weaker. Yeah, because it decreases with the square of the distance. In fact, remember 1 over r squared. If I were to sketch, G versus r, it's going to look like this. It's going to look like this. And so 1 over r squared. Yeah, and well, you get the idea. Yeah. So this is the gravitational field produced by M, and the capital M, that is, and the magnitude is inverse proportional to the square of the distance. The further away, the weaker it gets. So then, let's say that if you put an M here, then all you need to do is, once you calculate Gm over r squared, let's say this is r, let's say it's called x there, this is x. Now that's the gravitational, field strength at a location x away from this capital M. Then you multiply lowercase m with g to get the force, and that's equal to Gmm over x squared, which gives you back the now familiar expression for the gravitational force between the two masses in this example. Now, one example that we can examine is this. Let's say that you have two masses. They produce their own gravitational field in their vicinity. So the question might be asked is, at what point during the line joining the two masses is the gravitational field strength 0? Now, let's say that they are separated by a distance d. Now, this is actually similar to what the example that we discussed previously for force. The only location that in which the gravitational field strength is 0, it's gonna be in between M and M. Now, it cannot be here. Let's say here, if it's located here, then we know that the gravitational, the gravitational field strength due to M, it's gonna be this way. So this is G low M, and uppercase and lowercase m. And then here, also due to that m over here, is going to be this way. So you know that they cannot possibly cancel because they are going in the same direction. Now remember, gravitational field, you can see that the direction is always, it's directed radially outward. Radially inward. So meaning that it's always point towards where the source mass is. So the source mass is here. So at this point, the field strength or the field is produced. It's this way, going to this the location of the source mass number 1, and then also this is source mass number 2. So the gravitational field is also pointing that way. So that these two, you know that they cannot possibly cancel, they will add up. So it's always going to be, in this case, in between the two. But where exactly the location? Now, in order to answer that, this is similar to what we did before for force. Let's say it's located here, or maybe here. So here, let's call this location to be X. Now, the question is, what is the gravitational field strength at this point due to M? Due to M, lowercase m, is this. Let's say this is G lowercase m, and then also the gravitational field strength at this point due to uppercase M is going towards capital M, yeah, the uppercase M, this way. And you know that they already opposite each other. So in order for the G to be 0, you only need to impose that the two must have the same magnitude. In other words, G M minus G capital M, 0. So G lowercase m, G capital M. Now G lowercase m is equal to G M, M lowercase over, now the distance is this. You remember that this x here is the distance between the capital M with this point over here. So then obviously the distance between the lowercase m and this point is d minus x. Yeah? So d minus x squared, and this is G capital M over x squared. And as always, we can cancel this, and then we can write capital M over M equal to, let me make it simpler. So lowercase m over capital M equal to d minus x over x squared. So square root of capital lowercase m over capital M, d minus x over x. So x root of m over capital M equal to d minus x. So x1 plus root of lower m over cap m, square root of that, d. So then the x is this. Now this expression is very similar to the one that we discussed before, and it shouldn't be surprising, because the only thing that distinguishes the force and the field is that field is actually force per unit mass. So here there is no mass here, so it's just a point of interest that we want to find the location in which the gravitational field strength is 0 due to both of these two source masses, capital M and lowercase m. Now let's start to discuss about gravitational potential energy and gravitational potential. Yeah. So in the second part of dynamics video, we talk about gravitational potential energy, right? We define it as m times g time h. So what this tells you is that if you have an object of mass m, and let's say that it is located at distance h from the ground, then the gravitational potential energy is equal to mgh. Now, while this is true in everyday, a lot of everyday situation, because daily we deal with height of vertical distance that is much less than 1 kilometer from the sea level or from the ground. Yeah, but the thing is that from the previous discussion, we know that this G, let's say that if this is the Earth, right? And Earth has a radius r, capital R, okay? If this is h, then if we calculate G equal to for Earth, Gm over r squared. Now this will give you, this is 6.67 times 10 to minus 11. The mass of Earth is approximately 6,000, it's actually 6 times 10 power 24, yeah? About this. So in the neighborhood of this approximate, okay? And that the radius of Earth is 6,380 kilometers, so it's 6.38 times 10 to the power of 6 meter, and then you square it. So this will comes out as approximately 9.81. So this is the value that we use for gravitational field strength for a lot of discussion in kinematics and in vertical motion, yeah, 9181. Now if the distance is actually h away, h above the surface, then what happens is that the g should have been g capital M over r plus h square, right? So it cannot be this. However, if this r here, r is 6,380 kilometer. So if h is only like 1 kilometer or less, then if you substitute that number here, it's not going to give you much difference. So it's not going to be appreciably significant. So then that's why for a vertical distance that is actually less than 1 kilometer or about 1 kilometer or less, we can assume the g to be constant. Now here I'm going to show it to you how this equation works. But then in order to do that, we need a mathematics of binomial expansion. So for you, if you're not familiar with binomial expansion, you can actually skip this part. But if you want to just look at or learn how to derive it anyway, you can also do that. But by the way, the proof is actually not necessary. Yeah. So again, I just want to show it to you how you get that expression from the expansion. So how does it work? Okay. So in order to calculate the GPE according to what we defined GPE before, which is what do you call it? What we defined before, GPE was defined as this. Yeah. So you multiply mass, g, height, vertical distance. But remember, the vertical distance is always with respect to a certain reference point. Now the reference point that we use is the ground, yeah, or the sea level, but it doesn't have to be. Yeah. Now, so therefore, the GPE in this case is actually this GPE should be defined as the difference between the GPE at this point, point that is h from vertical distance away from the surface with the GPE at the surface. So the difference. Yeah. So in other words, in order to calculate this GPE, this is equal to the gravitational potential energy at h plus r minus the gravitational potential energy at r. Yeah. Now, so what is the general definition of gravitational potential energy? So potential energy is energy due to interaction. So if you have two mass m1, m2, you are located at a certain position from each other, the potential energy is actually defined as the work done in order to bring the two objects, yeah, so that to bring the two objects from infinity to a point that is distant r away from each other. So let me explain. So let's say you have m and capital M and lowercase m. Now they are at a certain distance of r from each other. So you know that there's a gravitational force between them. Now question is, yeah, if initially they are separated by a distance that is infinite, so they are actually separated by a very large distance that to the point that we can identify the distance, that very large distance, as infinity, then because of the attractive force, then they will eventually get closer and closer to each other. So the question is, what is the work done in order to move the force, to move the two masses so that they are distant r away from each other? Now in order to do that, remember that the gravitational force is given by G capital M lowercase m over r squared. Now if I were to sketch the force versus the position, like r is distant between them, then from this equation, then obviously it's going to look like this. Yeah. Okay. Now initially the distance between them is infinite. So then you want to know what is the distance required, so that now they are at a certain distance r away. So this is r prime, let's say, and this is r is the specific distance, yeah, between them right now, and this is like, you know, r in general, r prime in general. So that in this case, in order to calculate the work done by this force, you need to calculate the area under the force versus position graph. Yeah. Now, in order to calculate the area, if the area is not any shape that you are familiar with, then you know from calculus you can do that by integration from infinity to r of the force versus the forces that as a function of distance, dr. Okay, so now again, this is also one part of the aspect of this that you don't have to worry about too much. What you need is actually the final answer, because this requires calculus. Yeah. So if you if you integrate, the answer is going to give you minus g m over r. Yeah. So this is the work done from the work done by the gravitational force, so that the two masses, which are initially at, you know, a large distance from each other, so that they are now moved towards each other and at a distance r from each other. Now this is the definition of gravitational potential energy between m and m at distance r. So this is, so the gravitational potential energy of m and m separated by distance r is simply the work done by the force, yeah, the gravitational force to bring two masses, yeah, together from infinity to location such that the separation is r. The separation is r. So now the separation is r. Yeah, so g minus, remember there's a minus sign here. Yeah? So the minus sign does not indicate direction at all, yeah? Because remember, gravitational potential is scalar. Yeah? So this minus has something to do with the negative work done. Okay? Now, with this definition of GPE, then let's go back to what we discussed before, which is to calculate the GPE at point h plus r, and then GPE at point r. So we subtract, and then once we subtract, yeah, then we can see how the expression that we are familiar with before, GPE, which is mgh, is approximately a good what do you call it, a good replacement of this formula, a good substitute, but obviously in the case where h is much less than r. Okay, now let's look at the equation for GPE at h plus r. So you know what, let me just erase some here. Now, let me erase this because we don't need it now. Okay, yeah. So then the GPE at h plus r is, let's say that there's a mass, this mass is here, is equal to minus g m over h plus r, and the GPE at r is minus, so obviously when I say GPE, I mean the gravitational potential energy between the center of the Earth and the center of this mass, this object, g m over r. Then we need to subtract. Now, when we do this subtraction, before we do any subtraction, let me, let me do some algebraic manipulation. Yeah, let me just erase this first. Let me manipulate this a bit, right? As Gm m over r, and then you have 1 plus h over r here. Yeah, so, and then the GPE at point r is minus Gmm over r. So then if you do the subtraction, the GPE, the previous definition of GPE that you are familiar before, yeah, is equal to this minus that. Yeah. So this is minus Gmm over r. Okay, and then you have like 1 over 1 plus h over r, and this is minus 1. Yeah, this minus that, so it's minus 1. Now here we have the expression 1 divided by 1 plus h over r. Yeah, so let me use this part of the board to show it to you. So 1 divided by 1 plus h over r can be written as 1 plus h over r power minus 1. Now, if the h over r is less than 1, much less than 1, then we can actually use the binomial expansion approximation to replace this expression here. Yeah. So if you remember binomial expansion with negative or fractional power, 1 plus x power n is equal to 1 plus nx plus n minus 1. Now, obviously, if you learn, if you're doing mathematics high level, the analysis stream, then you're probably familiar with this. Yeah? So this is becoming using this, and obviously the approximation, the power will go up indefinitely. However, since x is much less than 1, this expression is much less than this, this expression much less than this, then we only need to look at the first few terms, because of the increasing power of x will make it even smaller and smaller and becomes insignificant. So the 1 plus h over r power minus 1, this is going to give you 1 plus the n is minus 1, x is h over r. Okay, now in this case we don't really need this term. Yeah, this term is going to be much too small compared to that. So then this becomes 1 minus h over r. It's that simple. We don't really need to look at this, because here the quadratic term, you will wind up with h square over r square. Now h over r itself is already much less than 1, so it's like the height of this is much less than the radius of the earth. Yeah, so why do we need to include the square term? The square term is just going to be like much less and become like, it's only going to add like more decimal place without appreciably change the outcome. Okay, so this is 1 minus h over r. Yeah, so then from here, let's substitute the GPE here becomes what? Minus, let me just use approximate, Gmm over r, and this becomes 1 minus h over r minus 1. So you can see that the 1 and minus 1 cancel, and there's a minus, multiply with that minus will give you positive, which is Gmm over r square times h. Now remember this term, the Gm over capital R square, what does it give? What is this? Now this is we discussed before, this is the gravitational field strength produced by Earth, yeah, because Earth has mass capital M at the location right on its surface. That's why R, yeah. Now, the value is obviously G. Now remember, I erased that before. I think I wrote it around here. I wrote like this. This is the gravitational field strength. Yeah, gravitational field strength at the surface of the Earth. Yeah, because remember the R here is obviously the radius, yeah, calculated right from the center. So this become G, so mgh. So then there you go, you see that the normal, the regular definition that we have for the GPE, as in the previous video before, for everyday life situation, which is simply mgh, is actually just special case, yeah, a special case of a more broader and more general definition of GPE. So I hope you understand this derivation. The derivation is actually not that important, but I hope that you can understand how this is related to that one, yeah, to the more general definition of gravitational potential energy. Last, we want to talk a bit about gravitational potential. Yeah, so remember the terminology for the previous subtopic was gravitational potential energy. Now we're dealing with gravitational potential. Yeah, so this is the definition. So the gravitational potential energy at a certain point, yeah, this is equal to the work done per unit mass, work done per unit mass to bring a test mass from infinity. Infinity is actually defined as any location that in which GPE, gravitational potential energy, is zero, so far away distance. Yeah? Test mass from infinity to that point. So it's a function of I'm sorry, this is not gravitational potential, this is gravitational potential. Yeah. So gravitational potential is a function of location. So this, what do you call it? This position in this space is a gravitational field. So at every point in the gravitational field, there is gravitational potential in which values can be calculated by work done per unit mass. So in other words, you can just use the GPE divided by the test mass. Yeah? So this is minus GMM over R over the test mass. The lowercase m is usually used as the test mass. Yeah? So this is the gravitational potential. Again, you can see that there is a minus sign, but the minus does not indicate direction because it's a scalar. Yeah. Now, this is gravitational potential minus Gm over R. So in other words, let's say that you have mass 1. So by the way, this M is the capital M is the source mass, yeah, the source mass. So if you have like M1 here, M2 here, and then you have M3, and let's say that there's a point, and this point over here is R1 away from M1, and it's R2 away from M2, and it's R3 away from M3. Now, this being scalar, in order to calculate the potential, gravitational potential at this point, all you need to do is simply use this formula, so minus G M1 over R1, minus G M2 over R2, minus G M3 over R3, and then just add them algebraically like that. So there is no, there is no need for you to find the resultant because it's not a vector. So this is just a normal sum. So find the value, be negative or positive. Well, always negative, yeah, because remember, the mass and the distance always positive. So then gravitational potential is always a negative quantity. So you can see that you can just add them to get the gravitational potential at this point due to this configuration of these three masses. Okay? So if you were to sketch if you just look at one mass, yeah, so the mass is this, I'm sorry, this is the potential, yeah, so this is the gravitational potential as function of distance from the source mass, then you should expect that the graph should look like this, yeah, so like that. So it's negative, yeah, so 1 over r, minus 1 over r. I also want to point out that there is a relation between gravitational potential and gravitational field strength, yeah. So what are the relationship? Now, if you were to sketch the magnitude, yeah, if you look at the formula gm over r squared, this is the gravitational field strength due to capital M as the source mass, and then you have Gp, gravitational potential, which is Gm over R. Now, this seems to suggest that there is a relationship between them. In fact, if you are familiar with, again, calculus, yeah, you can actually find G from the differentiation of Gp. So in other words, if we were to sketch Gp or gravitational potential, the magnitude that is, so we only care about the magnitude, yeah. Function R, then, which is 1 over r, yeah. Then what happened is that the slope of tangent line, so the slope of the tangent line at any point, let's say here, this will give you the magnitude of the field strength. So mathematically we can write down G is equal to delta Gp. Let's say Gp or gravitational potential. Let's use a symbol, this symbol, gravitational potential over m. Yeah, so the magnitude. Yeah, so it's better to write like this. So magnitude of G equal to magnitude of that. Yeah. So in other words, field, yeah, is actually equal to a potential gradient. Now, it turns out later that when you learn about another type of field or force, yeah, this is also true in that case. So field is a potential gradient. Now, this knowledge helps you a lot to solve problems where you want to find where the potential is the greatest. So the potential is greatest, or yeah, well, the magnitude is the greatest, yeah, when the G is equal to 0. Yeah, so the point Z equal to 0. So that's it for our lesson today about gravitational force, field, potential energy, and potential. We will continue the discussion about circular motion and gravitation in the next video, in which we will bring together the concept of circular motion and gravitation in what we call as orbital motion. So don't forget to like, subscribe, and share the video. I'll see you again in the next lesson.